The formation of mountains is one of the most dramatic and awe-inspiring processes in the geological history of Earth. We see mountains as static, immovable giants that dominate the landscape, yet their formation is a dynamic process that unfolds over millions of years. Understanding how these majestic landforms arise is crucial to comprehending the complex and ever-changing nature of the Earth's surface. The intricate details of how mountain belts form and evolve can be challenging to grasp, particularly given their immense size and the vast timescales involved. However, using both natural observation and innovative scientific models, geologists have developed theories and experimental approaches to explore this fascinating process. Mountain formation, or orogenesis, is primarily driven by the movements of the Earth's tectonic plates. The Earth's lithosphere, which includes the crust and the upper part of the mantle, is divided into large, rigid plates that move across the surface of the planet. These plates interact with each other at their boundaries, and it is at these boundaries where most mountain building processes occur. When tectonic plates collide, they can either crumple and fold, creating towering mountain ranges, or one plate may be forced beneath the other in a process known as subduction. Over time, these interactions lead to the thickening of the Earth's crust and the eventual uplift of mountains. In order to better understand the complexities of mountain formation, geologists have turned to experimental models that simulate the forces and processes involved. One such model, developed by French geologist Jules Mavier, uses sand to mimic the behavior of rocks during mountain building events. While the natural process of orogenesis occurs over tens of millions of years, the sand models allow scientists to compress time and space, enabling them to observe the formation of mountain structures in just a few minutes. These models offer valuable insights into how the Earth's crust deforms, folds, and faults as it is subjected to the immense pressures generated by tectonic plate collisions. The basics of plate tectonics and mountain formation. The theory of plate tectonics provides the framework for understanding how mountains form. The Earth's outer shell, or lithosphere, is divided into several large plates that move relative to each other. These plates float on the semi-fluid layer of the mantle known as the asthenosphere, which allows them to move over time. The movement of these plates is driven by convection currents within the mantle, which are caused by the heat generated from the Earth's core. As the plates move, they interact with each other at their boundaries, leading to various geological phenomena, including earthquakes, volcanic activity, and mountain formation. Mountain ranges are typically associated with convergent plate boundaries, where two plates move toward each other. There are three main types of convergent boundaries that can lead to the formation of mountains. Oceanic continental convergence. In this scenario, an oceanic plate collides with a continental plate. Since oceanic crust is denser than continental crust, the oceanic plate is forced beneath the continental plate in a process called subduction. As the oceanic plate descends into the mantle, it melts, and the magma that is produced can rise to the surface, creating volcanic mountain ranges. A well-known example of this type of mountain range is the Andes in South America, which formed as the Nazca Plate subducted beneath the South American plate. Oceanic-oceanic convergence. When two oceanic plates collide, one is usually subducted beneath the other. This process leads to the formation of volcanic island arcs, which can eventually develop into larger mountain systems. The Mariana Islands and the Japanese archipelago are examples of mountain systems that formed from oceanic-oceanic convergence. Continental-continental convergence. When two continental plates collide, neither plate is dense enough to be subducted. Instead, the crust thickens and deforms, creating large mountain ranges. This type of convergence is responsible for some of the most impressive mountain ranges on Earth, including the Himalayas, which formed from the collision between the Indian Plate and the Eurasian Plate. The most well-known and studied examples of mountain formation occur at convergent plate boundaries. These areas are characterized by intense geological activity as the plates collide, causing the Earth's crust to buckle and fold. When two continental plates converge, they create orogenic belts, or mountain belts, which can extend for hundreds or even thousands of kilometers. The collision between the Indian Plate and the Eurasian Plate, which began around 50 million years ago, is one of the most dramatic examples of continental-continental convergence. As the two plates collided, the Indian Plate was thrust beneath the Eurasian Plate, and the resulting compression caused the Earth's crust to thicken and rise, forming the Himalayan mountain range. This process continues today, with the Indian plate still pushing northward into Asia at a rate of about 5 centimeters per year. As a result, the Himalayas are still rising, and the region experiences frequent earthquakes as the two plates continue to interact. The formation of mountains at convergent boundaries is not limited to continental collisions. In oceanic continental convergences, the subduction of an oceanic plate beneath a continental plate leads to the creation of volcanic mountain ranges. The Andes, for example, formed as the Nazca Plate was subducted beneath the South American plate. This process not only created the towering mountains that we see today but also generated the volcanic activity that is characteristic of the Andean region. Similarly, oceanic convergence leads to the formation of volcanic island arcs, which can develop into larger mountain systems over time. The role of faulting and folding in mountain formation. One of the key processes involved in the formation of mountains is the folding and faulting of the Earth's crust. As tectonic plates collide, the immense pressure causes the rocks to deform. Depending on the properties of the rocks and the amount of pressure applied, this deformation can take the form of either folding or faulting. Folding: when rocks are subjected to compressive forces, they may bend and fold rather than break. This process creates anticlines, upward arching folds, and synclines, downward trough-like folds. These folded structures are often visible in mountain ranges, where layers of rock have been pushed up and tilted by tectonic forces. In the Himalayas, for example, the collision between the Indian and Eurasian plates has caused the crust to fold, creating the characteristic ridges and valleys of the mountain range. Faulting: in some cases, the pressure exerted on the rocks is so great that they break, creating faults. A fault is a fracture in the Earth's crust along which movement has occurred. When rocks on either side of a fault move vertically, they create fault block mountains. These types of mountains form when large blocks of the Earth's crust are uplifted and tilted, as seen in the Sierra Nevada mountain range in the western United States. Both folding and faulting contribute to the overall structure of mountain ranges. In areas where the Earth's crust is thickened and compressed, folding can create large-scale mountain belts with complex internal structures. Faulting, on the other hand, can result in the uplift of individual mountain blocks, creating steep, dramatic landscapes. Jeux-Mavier's sand model, simulating mountain formation. While the natural process of mountain formation takes place over millions of years, it is possible to simulate these processes in the laboratory using models. One such model, developed by French geologist Jeux-Mavier, uses sand to mimic the behavior of rocks during mountain building events. Sand is an ideal material for these experiments because its deformation behavior is not dependent on time, allowing scientists to study geological processes that normally unfold over vast timescales in just a few minutes. In Mavier's sand model, different layers of sand represent different strata in the Earth's crust, such as sediments and the continental crust itself. By mixing the sand with a finer powder, the model can simulate the varying mechanical properties of real rock layers, with some layers being more resistant to deformation than others. This heterogeneous material allows the model to replicate the complex folding and faulting that occurs during mountain formation. In the experiment, two sand continents are placed on either side of a layer of sand that represents an ocean basin. As the model is compressed, simulating the movement of tectonic plates, the oceanic sand is subducted beneath one of the continents, and the two continents eventually collide. This collision causes the sand layers to fold and fault, mimicking the deformation that occurs in real mountain belts. The green sand, which represents the rocks of the ocean basin, is trapped between the two continents, marking their original boundary. This is similar to what happens in nature, where oceanic rocks are often preserved within mountain belts as remnants of ancient ocean basins. The sand model provides valuable insights into the internal structure of mountain belts, which are difficult to study directly in nature due to their size and depth. By compressing time and space, the model allows scientists to observe how different layers of rock deform during mountain building events. The folds and faults that form in the sand are similar to those found in real mountains, such as the Himalayas, providing a useful tool for understanding the complex processes involved in orogenesis. The role of erosion in mountain formation. While tectonic forces are responsible for the initial uplift of mountains, another important process that shapes mountains is erosion. Erosion refers to the wearing away of the Earth's surface by natural agents such as wind, water, and ice. Over time, erosion removes material from the surface of mountains, exposing the deformed rocks that were once deeply buried within the mountain belt. Erosion plays a crucial role in the long-term evolution of mountain ranges.